Today it is lecture number 35 and last lecture of this course, convex optimization. Again, I will discuss about algorithmic approach to deal with unconstrained, unconstrained minimization problem. So we had till now seen two kind of algorithm. One was general descent algorithm, in which I discuss gradient descent approach, or simply you can call it a gradient descent. You can write it in short form. GSD method, or GD method, simply you can call it GDM. And another I discuss about steepest descent method, DM. Today I will discuss in detail about Newton method and some shortcoming of gradient descent method. What kind of problem you will face when you will apply gradient descent method to any simple even quality kind of problem or by quality kind of problem. Then definitely it is not always possible to get solution of the given quality problem very fast, or any polynomial kind of optimization problem very fast using gradient descent method. So what kind of problem would be there, and some ill kind of situation we are calling it, that actually highly dependent on condition number of the problem. So I will introduce also conditional number as well. So those things I will cover in the part of recap of Astupes decision method. And when coming to Newton decision method, I will discuss in detail about Newton decision method and what is the stopping criteria. Here, a stopping criteria of Newton method, it will define in term of Newton decrement. So those things I will discuss in detail here. So you can call it as generally in a steepest descent method, most of the descent technique happens to be first order method, or you can say that first order oracle, one order oracle. And Newton descent method, you can say that it is a second order oracle or second order method, you can call it like this way. So coming to recap of a steepest descent method, I have taken here one problem, a simple kind of problem. So I will talk about convergence of that quadratic problem, and how convergence is influenced by condition number of that problem. Then here we are taking a very simple quadratic problem, that x transpose ax equal to ax. We are minimizing x transpose ax, where a is what? It is a positive definite matrix. So due to positive definite coefficient, this objective function would be always a what? It is a convex function. Even more than that, it is a strongly convex function. So we are trying to minimize a strongly convex function through over the complete domain, Euclidean domain Rn. So it is an unconstrained problem, and we know that if you directly solve it, and then what would be gradient of this one? Gradient of this quadratic function would be just a linear function, ax. You are finding gradient of this one, and we know that where is a what is the solution of ax equal to 0? One solution is a very trivial solution, that we are calling it 0. So this objective function is theoretically it is having optimal value at 0. So that's where, and what is the optimal value? 0. Optimal value of this quadratic problem is 0, and optimal point is 0, and it is a convex quadratic problem. So we know that from theoretical perspective. Now algorithmically, if you are trying to find this problem, then that one would be highly dependent on the condition number of a, how it will be. So I will introduce Cantorowicz law here in order to see the convergence relation of a given quadratic function with respect to condition number. So coming to gradient descent, a step of this problem. So using exact line search, I had already told that if you are taking quadratic function, then it is better to go for exact line search. Why? Because in exact line search you will get an explicit form of step size. So step size in gradient descent, directly you can get it an explicit form. It would be given by this formula. Okay, so it is just a solution of single variable problem, and due to with respect to this step size, you are getting this update rule: xk plus 1 equal to xk minus t times dk. Dk is the search direction, or you can say that a step gradient or descent step. And dk easily again if you are saying that what is decay, you can directly get it from the gradient. By taking gradient of this function at point xk, you will get decay. So decay is very simple to get because your objective function is what? It is a quadratic function. So what is the derivative of this one, this quadratic function? It would be 2 times ax. So that's where decay equal to 2 times axk at point xk. Xk is your current point. Okay, and also you are having explicit formula for step size. Also you are having uh, explicit formula for descent step, or you can call it search direction. Dk equal to a twice of a time xk. So you have everything here, everything looks explicit. So then what is the problem here? The problem is all about convergency. So how we can measure the convergency? So we will try to try find functional value at updated point xk plus 1. So what would be function value? So f of xk plus 1, you can directly uh, we can get it by substituting xk plus 1 in the objective function. So it would take form what? uh, x transpose xk plus 1 a time xk plus 1. Okay, and what is xk plus 1? We can get it from this update tool. Xk plus 1 is actually written as a current point xk minus t times dk. So substitute all these xk plus 1 here. After substitution, what you are getting? You are getting a this quadratic term, or quadratic form. You can say that what does it is? It is a value of the function at point xk, and that current point xk times what we here this factor we observe. These are quadratic in step size tk. You can see that it is a linear factor. This one is a quadratic term in tk on a t. Simply you can say that in t step size. Now, further, if you take common xk plus xk transpose a times xk, then what is remaining thing? Remaining thing you observe like this way. These are the remaining thing. 1 minus 1 by 4 times. I have taken a substitute. I have taken value of tk in term of the direction. This a step search direction and the function value, and it will take this form, this simple quadratic kind of form. And if you simplify it, then you can write it like this way: 1 minus this ratio, this ratio times all times f of xk. So you can easily observe that your function value at updated point or future point, it is expressed as some factor. This factor, call it c, c times or times f of xk. Then what will happen? Suppose if this factor c is less than 1, then definitely we will see that there would be decrement in the value of the function. If c is greater than 1, then we want to there would be convergence issue. That means there would be no minimization. So this factor which is coming in the bracket, it is very important from the convergence analysis. So in order to go further in detail regarding what kind of things are coming here, so I will introduce conditional two things. One is Cantor's theorem regarding a matrix, because matrix is involved here in order to define a quadratic function. So I will introduce Cantor's theorem and the condition number of a given matrix. So those two things I will introduce. Then I will come back to this convergence issue of the simple quadratic problem. Okay, any question? If you have any question, then you can ask. Otherwise, I will go further. Yeah. Anytime in between, if you are having any question, you can raise your question by asking, or you can put your question there in the comment box as well. I would like to answer later. So, what is Cantor's theorem or Cantor's inequality? Cantor's inequality, it says that if you are having a positive definite matrix, that one is n by n positive definite matrix, then for any non-zero vector x, n dimensional non-zero vector x, we observe the inequality. That means ratio of square of x transpose x divided by x transpose ax into x transpose a inverse ax. So what is so both are related. It is inverse of a. So this ratio, it is what? It is a ratio of two quadratic function. I simply say This one is also quadratic function. This one is also quadratic function. We know that it is a quadratic form. Why? Because and it is always a positive quantity. Why? Because A is a positive definite matrix. Similarly, if A is a positive definite matrix, then inverse of a positive definite matrix is always a positive definite matrix. So that's why second term is in the denominator is also a positive quantity. So all these quantities, these two quantities are positive, and we know here you observe a square of x transpose x. So a square of any non-negative, non-zero number is always a positive number. So overall, you can say that this ratio is a positive number. You can say that, or greater than equal to zero. Then this quantity, this ratio of this quadratic function, to quadratic function is always bounded below by this term. That means product of maximum eigenvalue of the corresponding positive definite matrix into minimum eigenvalue of the corresponding positive definite matrix. Why? We know that here is a positive definite matrix, so every eigenvalue of this matrix would be what? Always greater than zero. There would be no zero eigenvalue. A will have, neither it will have negative eigenvalue. Only what kind of eigenvalue A will have? Only a positive eigenvalue it will have. Why? Why? Because A is a positive definite matrix. So this ratio of quadratic function is always greater than equal to or bounded below by 4 times maximum eigenvalue of A times minimum eigenvalue of A divided by uh, square of sum of maximum eigenvalue of A and minimum eigenvalue of A. So this quantity is a, it is a, you can say that it is a deterministic kind of quantity if you know about A. If why? A is a coefficient matrix, that means you know about A. So if you know A, then you can calculate the lower bound of this ratio. Easily you can calculate it with the help of eigenvalue of A. Easily you can calculate. So this inequality we are calling it Centrovich inequality, and it is playing very important role in the order of establishing convergency of a convex quadratic uh, optimization problem. Okay, so coming to this one further, if you do little bit manipulation, you will see that this ratio, right hand side ratio, easily you can express in term of kappa. Kappa would be what? Kappa, I will call it conditional number of the matrix. What is conditional number of a matrix? It is talking about ratio of the maximum eigenvalue of a matrix divided by minimum eigenvalue. So this I will call like this. K don't consider as a iteration number k. It is kappa. Kappa means a Greek word. It is introduced in order to define conditional number. So here I am calling kappa uh, ratio of maximum eigenvalue of the given matrix A divided by minimum eigenvalue of the matrix. If this kappa is very big, then the problem we will call it ill-posed problem. If it is reasonable, it is taking reasonable value, then we will call it easily we can solve that problem with the help of gradient descent, and convergency is very fine. Coming back to the convergence analysis of the last problem, that quadratic convex problem, how we can do? So using this Cantorowicz inequality, we can get that the functional value at this updated point xk plus 1, it would be less than equal to uh, this factor, okay, times here x times f of xk would come here. And if you do little bit modification of this ratio, what is I have taken here capital M is what? Capital M is denoting maximum eigenvalue of the given matrix. Maximum eigenvalue of the given matrix, coefficient matrix A. And a small m is here, it is a notation for least eigenvalue of A. Okay. So further, if you simplify this 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 right hand side expression, it will take this form: a square of kappa minus 1 divided by kappa plus 1 times f of xk, where what is kappa? I have already given definition. Kappa is ratio of capital M divided by a small m, or ratio of maximum eigenvalue of A divided by minimum eigenvalue of A. Okay. So this up now your convergency is highly dependent on this ratio, a square of ratio. So call it C square. So easily you can observe that f of xk plus 1, f of xk plus 1 is always less than equal to C square f of xk. Okay, suppose C is less than 1, then we can talk about convergency of this problem. That means there is a decrement in the function of value. If C is not less than 1, it is greater than 1, then we will talk about there is issue, certain issue. So one a special kind of function here I have taken it, Rosenbrock function. You can observe that for Rosenbrock function, conditional number is very high. So there are various form of Rosenbrock function. One function I have taken it here in a biquadratic form, like 100 times a square of x2 minus x1 square, okay, plus a square of 1 minus x1. So it is a very famous optimization problem. We are minimizing this problem, this Rosenbrock function with respect to x, and this one is an unconstrained problem. And what is the minimum value of this one, or optimal value of this one? Optimal value of this one is 0. And what is the optimal point? Optimal point is 1 1. Okay, so it looks nice. It looks it is a polynomial function. We can easily optimize. It may look like that. But if you are willing to apply gradient descent, then you will face problem. It will take several iteration in order to converge to optimal point, or in order to get optimal value. So why? It is all about due to bad behavior of the Hessian near optimal point. So what we observe here, we first have to find the Hessian of this problem in order to know, in order to use this gradient. So we are finding gradient first, then we are finding Hessian. So I have already calculated gradient and Hessian. You can observe that. So gradient is again, it is involving quadratic function in this entry, and Hessian, this is the Hessian. And by solving this uh, gradient directly, also you can get optimal point. One would be optimal point, and it is having only one stationary point, 1 1. So by default it becomes a global minimum of this problem, and it is not difficult to solve that. I would like to x11. Okay, 1 1 is the unique stationary point for this given Rosenberg function. And here if you calculate kappa, that means if you calculate conditional number for this problem at point 1 1, that means we know here what we observe. Here we observe that here Hessian is, it is a function again, it is not a constant Hessian. It is function of x1 and x2. So that's why it is not easy to calculate Hessian uh, kappa directly. So we will calculate kappa pointwise because it is a function of x. So we are calculating kappa at point 1 1. That means we are calculating condition number of this problem at point 1 1. So if you calculate condition number, it is around 25 2500. So that one is a very big number. So definitely this big condition number will have a severe effect on the convergence speed of the gradient descent method. And that means it will take time to converge the optimal point 1 1, and it will take several iterations. So I have taken this one initial point 25. You can look it to here, and how many iteration it is taking to converge 1 1 with optimal value 0. It is taking several iteration, almost around 7,000 iteration. It is taking almost around 7,000 iteration. And how you are visualizing? You are visualizing by observing this stopping criteria. This gradient of norm happens to be very less than some tolerance number. So this is you can define this kind of tolerance number. So epsilon, you can define it like that way. So you can easily that you can see that it is taking around approx 7,000 iteration in order to converge 0 0. But from the function itself, it looks that it is a polynomial function. So easily we can say that what is solution of this one, this given problem. But if you go try to solve algorithmically due to higher kappa or the higher conditional number, it is taking several iterations to converge the optimal point, near about optimal point. So it is there is a problem issue with the gradient descent method due to condition number. So it is really very much influenced by high condition number. So that's where sometime definitely you will face problem with gradient descent. And today, just to overcome that kind of issue, I have I would like to discuss Newton method. Newton method is not having such kind of issue. That means it is higher condition number is not going to affect Newton method. It is just independent of that. Even one more thing also you can observe with gradient descent is that gradient descent is highly influenced by change of coordinate. If you change the coordinate of your system by using any affine transformation, then definitely that will influence your gradient descent method. It is not good for that means gradient descent method is not affine invariant. But if you come to Newton method, it is affine invariant. So in order to understand Newton method, I am here defining two things. First, I would like to define Newton descent step. The Newton descent step, if we are trying to relate it with general descent technique, then it looks just one extension, one a special case of general descent method where we are taking Newton step or search direction. How we are taking, we are defining in terms of inverse of Hessian times gradient. So this is we are calling it descent step or direction, Newton direction, Newton descent step, or simply we can say that Newton's search direction. Okay, what is meaning of this one? So it says that uh, x plus this Newton of step or such direction, it always minimize the function, or you can simply say that minimize the function. What directly it is not minimizing the function, it is minimizing the second order approximation of the function. Second order approximation of the function. So if you are applying Newton methods, like what is the second order approximation? So suppose you are at current point x, and then you are getting as descent direction or such direction v. V is such direction. So what is the functional value at x plus v? Because here current point x you are taking as a reference point. So that's where you are just trying to approximate the functional value at x plus v by this approximate function, quadratic approximation. What is that? That one is f of x plus dot product of gradient with v plus uh, 1 by 2 into v transpose Hessian at x time v. So v is such direction. You are looking for a suitable such direction. So that such direction you will get using this Newton descent step. So geometry you can look like this way. This one is your actual function. You can look like this way. This is your actual function f that we denoted by f. And if you are taking quadratic approximation of this given function, quadratic approximation is given by f cap here, or f hat, you can read it like this way, f hat. So f hat is coming like this way. So it is a very nice function. It is a simple quadratic function. So you know if it is a quadratic function, then easily you can find minimum of this function. Where would be minimum? Minimum, that minimum you can say that it is a Newton minimum function. Newton minimum. So it would be at this point. This is the minimum. It looks convex in nature if you observe closely. Okay. And if you are willing to visualize it from derivative perspective, that means anyhow you are willing to solve in order to get optimal point. You are willing to solve that gradient of f. You are trying to find all those points where gradient is vanishing. That means gradient of f equal to 0. So if you take actual function and you find the derivative of that function, and that means gradient of that function, and if you plot where is the gradient is 0, at this point gradient is 0. But if you are taking just a quadratic approximation, and for that quadratic approximation, where is gradient vanishing at this point? So definitely clearly you can see that this one is your exact solution or exact optimal point, but this one is approximate solution. So you Newton method is always giving this approximate solution. Yeah, now we can say that if function is quadratic, then the gap between this approximate solution and exact solution, it will minimize. But if it is not quadratic, then definitely gap would be larger. So further here, what coming to Newton descent step. So we have already defined Newton descent step. So better I will call it NP. delta and t, Newton descent step. uh, it is the steepest descent with respect to a quietic norm. It is a steepest Newton. So Newton descent step is also a steepest descent direction with respect to what kind of norm? With respect to not L2 norm. With respect to a new norm, that also you can call it Hessian norm, or you can call it quietic norm. Remember that in order to define quietic norm, you need a positive definite matrix. So in place of positive definite matrix, we are taking Hessian of the function. Hessian at that point, current point at. So that's why Hessian norm is nothing, just it is a one kind of a quietic norm. So Hessian quietic norm, we had already defined what is that? It is a square root of y transpose p times phi. P is here Hessian, so it is defined like this way. So you can say that in Newton descent step, it is the steepest direction at x in term of Hessian norm. Okay, geometry, if you are willing to visualize, so geometry you can visualize like this way. So x naught you are taking uh, initial point, then you are performing one Newton descent direction. So that one is you can say that it is also acting like a steepest descent direction. Okay, so basis line here, if you observe basis line, it is all contour of the or contour curve or contour line of the function, and ellipse it is defined by this formula. Okay, equal to 1, and arrow, what arrow it is giving? It is talking about that descent direction. It is talking about negative of gradient, but exact descent direction you will come through steepest descent. It is just a descent direction, one of the descent direction. If you are taking negative gradient, one of the descent direction. But what is the steepest descent direction? This is the steepest descent direction you will get with respect to this Newton descent step. So it is giving a faster convergence. So coming to one more term in Newton method, that we are calling it Newton decrement. It is also very useful in order to define a stopping criteria. In gradient descent, you had already seen that what was the stopping criteria. In gradient descent, a stopping criteria was a norm of gradient at point, iterative point. It is always less than some tolerance number, that we are calling it epsilon. It should be very less. Norm of epsilon is less than equal to epsilon. That one was the stopping criteria for gradient descent method. Now coming to Newton method, then in Newton method we are defining stopping criteria in terms of Newton decrement. So what is Newton decrement? Actually, Newton decrement, it is defined as the value of the second derivative in the direction of gradient. So that means you can say that it is a square root of mm, a square root of, or simply you can say that norm Hessian norm of gradient. Another way that when you it is Hessian norm is one kind of quadratic norm where your positive definite matrix or coefficient matrix is directly coming from the Hessian. So that's way you can say that Newton decrement is nothing, just it is what it is. You can say that it is the value of the it is the Newton norm value of Newton norm of gradient. You can say that like this way. What does it do? It measure the proximity of x near to optimal point. How much near x, your x is near to optimal point. So you can say that it is one Newton decrement. Geometrically, you can say that it is a measure of proximity. So what does it gives a, so this Newton decrement, it gives an estimate of uh, the function value. It is how much away from the optimal value p star using a quadratic approximation f hat. So so same thing, how we can see that so f of x minus the minimum value of this quadratic function, it is equal to 1 by 2 times a square of Newton decrement. Okay, so this you can say that one kind of things. It say that it will one of the estimate of f of x minus p star. P star. If it is very less, then we will say that our step Newton step is very near to the optimal. Okay, So everything here I have already defined. Again, I'm recalling it. So now we have directional derivative. So we can say that if you further you would like to talk about another meaning of Newton decrement. What does it say? It is talking about the value of the directional derivative, value of the directional derivative in the direction of Newton descent of step. So it is what I had already defined. Directional derivative. How we define directional derivative? It is always talking about the dot product of gradient with a given direction. So dot product gradient at point x with a given direction. So direction, suppose here this we are calling it directional derivative. So here we have taken Newton descent step. So that's way if you try to find a directional derivative in the direction of Newton descent step, then you will come across to see it is what it is giving negative of the Newton decrement. So Newton decrement is also it can be defined as the directional derivative in the direction of Newton descent step. Now coming to algorithm of Newton method, I will describe here algorithm. What is the algorithm of Newton method? So here you can see that systematic algorithm for general Newton method, or simply you can call it here Newton method. Okay. So again, that's a similar fashion. What is the input? You have to take any input as a tolerance parameter that epsilon greater than equal to 0. This we are calling it tolerance parameter. It will help to define a stopping criteria or have to help to control a stopping criteria. Then we do perform initialization by taking a starting or initial point. It must come from the domain of the function. It is not like that you will take any arbitrary kind of epsilon. But here your problem is what unconstrained problems you can take. So domain complete Rn is the domain of the function. Then we perform general step, or you can say that you are performing a loop kind of. There is a loop where k is vary from 0, 1, 2 to it will keep on varying. Now here in this algorithm you can observe that you need to determine two things. First, you have to determine what is the Newton step or what is the Newton search direction. So Newton search direction it will be given by uh, negative of inverse of Hessian times gradient. That's one. Then once you are having Newton descent direction or Newton search direction, you will try to calculate Newton decrement. Why? Because you will use this Newton decrement in order to get a stopping criteria. So Newton decrement lambda it can be defined as you can say that it is easy to define a square of Newton, because here then that time right hand side you want to observe a square root. So a square of Newton decrement it is equal to what? It is the you can say that value of second derivative in the direction of gradient, or you can say that Hessian. You can simply say that it is Hessian norm of the gradient. Another way simply you call it Hessian norm. It is not as simple as L2 norm, it is Hessian norm, because we define this quantity norm with respect to Hessian. So you can say that Hessian norm of the gradient, that is giving the square of Newton decrement. Norm of gradient. Okay. So you have calculated two things here, Newton step and Newton decrement. Now, in next, what you will do, you will perform line search. So line search you can perform either by backtracking or either by uh, exact line search. So whatever you want to proceed, you can go for that. And remember that in performing Newton that line search, you remember that function must satisfy this condition that f of xk plus 1 must be less than f of xk. Now, using this one, this Newton step and this step size, you will define your next update by this formula. That means xk plus t times this Newton step. Okay, so this is the update rule. Okay, and it will keep on repeating until what? Until you meet a stopping criteria which says that lambda square by 2 is less than epsilon. So this is the stopping criteria for Newton method. It is different from gradient descent method. In gradient descent, we had that norm of gradient is less than epsilon. Here, just we are defining a stopping criteria in terms of Newton decrement. So that's why it is really very interesting. Okay, one more thing you will observe that while performing Newton method is always affine invariant. That means you are free to change coordinate of the system. Always it is independent of any affine change of coordinate system. So one example here I have taken it here. So Newton iterate for suppose you are performing a change of coordinate by this way. So you had initial coordinate system in term of x, then you apply some kind of transformation, and you are willing to apply bring some kind of invertible transformation. So generally change of coordinate transformation always happens to be invertible transformation. So we are saying that x equal to t, we are taking t of y, then also it can be written as a inverse, because always every coordinate transformation happens to be invertible transformation. That's why inverse y equal to, you can write it t inverse of x. Okay, t inverse of x. So here, what would be a starting point for this one? So a starting point, y naught, it would be just inverse image of x naught. Take this is the starting point. And what is the current iterative point? Current iterative point, it would be yk. So yk is nothing, just it is current inverse image of the current point xk. Then you may ask one question, why we are performing this kind of transformation or change of coordinate? Because sometimes you can see that anisotropic kind of contour of the given function. So it is not looking nice, but if you so it is a little bit elliptical kind of things. So always you can apply a fine transformation by, and through that you can convert this elliptical kind of situation into circular kind of situation. And in circular thing, you always observe that convergency is very fine. So in one step, Newton may converge there. Newton method may convert there to solution. Okay, so this situation always look fine, but this one may look a little bit complicated. And when something more drastic kind of situation you will observe in the contour plot. Okay, so this situation doesn't like good. So you always apply some kind of affine transformation or linear transformation, which would be invertible. So you can always convert into this nice kind of situation in this symmetric situation, and there you can apply for Newton method with respect to transform in transform a space, and things would be very simple. I would like to discuss about classical convergence analysis. Regarding classical convergence analysis, for any general descent kind of algorithm, always we used to assume few conditions. First assumption I am taking it here, that a strongly convex on the given domain, and that a strongly convexity will have certain parameter m. That means we are saying that the least curvature would be m. That given function can't be flat. It is definitely having some minimal curvature. That minimal curvature we are calling it m, minimal positive curvature. So m is here greater than 0. So that is meaning of saying a strongly convex. Second condition, we are putting that uh, gradient here, not Hessian. Gradient of the given function must be uh, Lipstick in nature, so that it not behave abruptly. So always a gradient norm of difference of gradient, it is controlled by this number L times difference of the norm of x and y. Okay, so due to this, that gradient behave very nice. This L, we can say that it measure how well f can be approximately uh, approximated by a quadratic function. Okay, so this L also you can see that it is measured by Hessian of the uh, problem, or you can say that it is somewhat L is related with measure of curvature. What is the outline of this assumption? So definitely due to all these assumption, there will exist a eta which is between uh, m square by L. It is similar to what you can say that what is eta? It is eta is your step size, and would be a gamma greater than 0, such that if norm of gradient is greater than theta, then we will see that the difference of the value of function at updated point xk plus 1 with current point is less than equal to negative of gamma, and if gradient norm of gradient is less than eta, then we can say that this ratio is less than equal to this quantity. Okay, it is all about convergence and a classical convergence analysis of descent algorithm. If you are having any question, you can ask. Otherwise, I am going to wind today's class. And thank you.